Rihanna?
I don't know what it is. Just start playing.
I'm pretty sure it's Rihanna, isn't it?
Sure. Why not?
All right. So we're going to go over the midterm and then keep going with stuff. So let's see. Class average was a 72.94 on the midterm. Max value was 100. Min value was a 0. That must have been somebody who just didn't take it. Let's see. So there were 5 A's, 3 B's, 5 C's, 2 D's, and 3 F's. So not horrible. Decent grade breakdown. 470 is far more entertaining. Because I think actually the average for 470 is literally identical to this.
Let's take a look.
Okay, but the standard deviation is like some gigantic number.
Can we look?
No. Well, when I go over it, we can.
I can wait till Tuesday for that.
All right. So when I call your name, come up and grab your test, and we'll go over it. Levi.
I want to see the epic failures.
Christian. Emo. Curcio. Conkle. Katie. Katie. I didn't call you yet. What did you think I heard?
He definitely did.
Totally called me.
Yeah, you for sure called him.
No.
I was confused if you had
I think I
said
said Katie. Not you heard me say Randy.
Yeah.
I would never call you that.
Holy shit, Katie.
Austin. Largen. Joel. Schumacher. Dover. Sean. So is it Zarnecki? Oh, that's on my. See, look at that talent. Zach. Doctor.
Did you sign in as doctor or
No, I put my name on it.
your name is doctor?
Sam. Looter not here. Ian. All right. Everybody got their exam back that took their exam? All right. So let's go through these. Dun, dun, dun. Once again, I will compliment you on the embarrassment of how many people missed number 1. Just complete garbage. All right. So I'll show you initially the.
Show us number 1.
Well, we're going to do all of them, but I'm going to show you the way I intended for you to do it. Then I'll actually show you the cool shortcut way that if you are... How many of you have had 325 in here? Architecture? Did you also miss that number 1?
Yeah.
Aye.
I was on narcotics. A lot of them.
Aye.
I get to school, I take my drugs, and then I come to class.
All
Best
right.
idea before midterm.
Well, at least it's before after you drive.
Yeah, that's what I take when I get here. Because like right now, they're starting to kick in. I took them 20 minutes ago.
I'm just going to... I'll just kind of throw it in here somewhere. The solution. All right. So midterm. Number 1 was to do what? Convert the number 110101111 from binary to octal. So this guy here, this is the ones place. This is the twos. Whoa, hello.
You went back to?
This is the ones place, the twos place, the 4s, 8s, 16s, 32s, 64s, 128s. So this is 128 plus 64 plus 16 plus 4 plus 2 plus 1. Okay, and then what is that?
215.
Is it 215? Is that, can I trust you in that? Is that what it is? All right, so this is 215. So the very first thing I would do is I would convert that binary number. This is what I intended for you to do, is convert that binary number into decimal. So now we have 215. Now we're going to convert that 215 into octal. So we're going to say 215 divided by 8. 215 divided by 8 is what? It's 26. 26 times 8 is 208, so that's a remainder of 7. 26 divided by 8. 8 goes into 26 how many times? 3 times is 24. What's remainder 2? 8 goes into 3 0 times with remainder 3 for a final answer of 327. Read it from bottom up. All right, so you want to see the fun way of doing this now? You can break this binary number up into 3s. So this is 1s, 2s, 4s. So this is actually the number 7. So 111 is the number 7. Huh?
Oh, you mean in that?
Just in that little 3. 111 is the number 7. 010 is the number 2.
And 3.
011 is the number 3.
I literally don't know how I got that wrong because all of my work is correct.
Yep. So the punchline here is that this kind of shows us why octal is a common thing in computers, is you can move between binary and octal pretty easily. And we talk about that in 325. We do binary to hex. Remember when we deal with nibbles?
Yeah.
Every 4 buckets. Octals we can deal with, I guess they're half words, 3 bits. And that allows us to go to octal. But my intention for you was to do this. Convert it to decimal, then decimal to octal. All right, kind of showing me that you understand how to do both sides of that conversion. And I think like less than half of the class got it right, which is, All right, so that's number 1. Number 2, what does it mean to say that Android is fragmented? How does iOS compare? Okay, so fragmented essentially means that we have a whole bunch of different devices with different screen sizes, different processors, different GPSes, things like that. And we have one operating system that has to be built to run on all of those different things. So the Android operating system itself is fragmented because it had to be designed to run on so many different things. All right, so then we talk about iOS. How does iOS compare? So something along the lines of, I mean, you could certainly say it's less fragmented than Android, but certainly it's probably fair to say that iOS is more fragmented now than it used to be. We have more different size screens on iOS than we had before, and now you no longer hear Apple really complaining about fragmentation.
But slightly more controlled in terms of the OS, because they control their handful of sizes.
Well, fine. So Apple controls so you can say Apple's less fragmented by default because they at least control the software development side of things as well as the device side of things, but it's still, you have different size screens. All right, so that was number 2, something along those lines. Difference between volatile and non-volatile memory. So this was kind of our RAM versus hard drive type thing. So volatile is memory that is, has to change very, very often. So this is going to be like our RAM, our registers, our caches. These are all volatile memory. Volatile memory typically is higher speed. more expensive per byte, whatever you want to think about it, and built to change often. That kind of goes hand in hand with the speed. Non-volatile memory, like our hard drives or tape drives, things like that, these are for longer term storage, tend to be slower, tend to be less expensive per byte, that kind of stuff. All right. Questions on that one?
Could you also say that it, like, the data will persist through a power loss and non?
Oh yeah, that's certainly fair. Yeah. I mean, volatile memory is the way the data is held. It's held in a static field relative to electricity, keeping it there. So if you had a power outage, you would lose anything in volatile memory, but non-volatile memory stores memory differently. It stores data differently. It stores it on either magnetic tape, or flash storage actually works a little bit differently in how it does. It uses cells, but it's actually interesting. Flash storage works significantly more like volatile memory does. It uses cells with stored electricity, almost like a battery.
So does that mean, like, the overall life that you could store something in, like, flash memory without power would be shorter than, like, a disk drive? Or, like, a regular...
Probably technically, but I don't think that there's, like... It's not like a
huge number.
Yeah, if you like leave your flash memory thing unplugged for a year, I don't think you've lost stuff. Is kind of what I'm getting at. It doesn't take a whole lot of power. I think it's more of like a, I guess I kind of think of it like when you see these movies where like people are held in like stasis for a really long period of time. Yeah, it's
some guy clutching a flash drive.
Right. It's something like that where it holds a static charge, but it's compartmentalized. It's not draining it. That's just part of what holds the memory together. But for that one, something along the lines of one is for short-term storage stuff, one is for long-term storage stuff. Non-volatile is their hard drive-y stuff. Volatile is your other stuff, registers or system RAM, however you want to talk about it. What is a hardware register and how do they compare to alternatives in terms of speed, cost, and size? Funny thing is, this was also missed a lot, which is ridiculous. We've all actually written code dealing with hardware registers. We spent hours in here talking about hardware registers. So hardware registers are our fastest form of volatile memory, right? These are basically variables built in hardware that live right on the CPU. They are, let's see, how do they compare to alternatives in terms of speed? So they are the fastest. They probably cost the most by per bit or per byte, however you want to think about it. And they're usually the smallest in terms of size. Okay, so very fast, very small, very expensive. Those are hardware registers. Okay, and they are the way that another thing you could have said is something with the CPU uses them directly to keep track of the current state of a PCB. That's where it stores its variables, okay, in hardware. Okay, what is the purpose of a PCB? Well, it's a data structure. Process control block is a data structure for holding information about a single process, not a collection of processes. Those queues and things like that, those are the process scheduler, which holds collections of PCBs. So an individual PCB is a data structure for holding information about a process. That is program counter, current state of registers for doing our context switching in and out of the CPU, the data section for all the assembly code associated with that, that kind of jazz. So information related to an individual process. Make sense? Let's see. What is a system call and why do we need them? So a system call is the mechanism by which user programs can talk to the operating system or talk to the kernel. Remember we had the picture where it showed kind of a layer of system calls, so you almost can think about them like bouncers. It's that middleman you have to go through in order for a user program like Microsoft Word to actually create files, stuff like that, have the operating system do things on their behalf. All right, so what are the purpose of these guys? So on one hand, you can say security. We don't let programs talk directly to the kernel. We don't let them boss the operating system around directly. Instead, we have these programs, these bouncers that you have to go through that help filter who's allowed to do what, that kind of stuff. It also, sometimes, some of you said something which I thought was good. It kind of led us down the path towards this idea of the microkernel. that we talked about, where if we can get the operating system squeezed down into this little tiny size where all the really, really, really important stuff is in the microkernel, and then we kind of put layers outside of that that have various, that's where I really can start thinking about it like a bouncer, where we control access to that microkernel where the actual important stuff is in that one place, and the system calls allow us to get to that. So examples of system calls would be like the fork command, which allows us to generate a new process. Let's see, did we talk about any other system calls? Did we talk about signals or anything like that? All right, but in any case, that's what system calls are in general. It's not necessarily only related to I/O. Okay, so I think a lot of people kind of said it's specifically I/O. They kind of try to connect it to the waiting state for a process, but that's not completely wrong. But system calls have more to do than just input-output. All right, difference between a process and a thread. Okay, so this dealt with how CPUs give time to different processes. So when we have multiple processes, each process gets its own time on the CPU. All right, so if we have 3 processes, if we go human version of fairness, each of those guys is going to get 1/3 of the CPU time. If one of those processes forks, which creates a brand new process, now you're going to have one of those starting processes actually getting 50% of the CPU time, because they're going to have 2 processes that belong to the same thing that each get their own CPU times. Now, those 4 processes are each getting 25% of the CPU time, which ultimately is going to give that one initial process 50% of the CPU time. So punchline here is a process is a heavier weight thing that is scheduled by the CPU scheduler and the process scheduler. Okay, so they get their own allotment of time on the CPU and that kind of stuff, which can be dangerous. All right, that doesn't mean it's bad. It just means that it carries, with great power comes great responsibility. If you have a program that spawns off 30 copies of itself as full processes, you just took a lot of CPU time away from other programs. Okay, some things that might be okay. I think we used in the class, like the example like Photoshop or something like that. It might be okay for us to have Photoshop have 2 or 3 different processes, because maybe if we're using it, we want it to have a little more CPU time because it's a CPU kind of intensive application. As opposed to threads, threads are kind of worker bees. They're lightweight processes, and they're actually controlled by the parent process that spawned them. Okay, so a thread is not a complete separate process. It's a sub-process within a parent process. And each thread shares in the parent process's CPU time. So if a parent process was getting 33% of the CPU time and he spawns off 1,000 threads, he's sharing his 33% of the CPU time with those 1,000 threads. Each of those guys does not get their own CPU time. Make sense? So that's a little bit more self-contained. They're lighter weight, so we don't need full PCBs to support all the stuff. Because now we're putting it on the individual process who has the threads underneath them to manage it. So they are lighter weight. It doesn't impact the rest of the operating system, but it still allows an individual process to engage in non-blocking, productivity. So you can have aspects of your application that are doing things in the, quote, background from a human's perspective, right? Because the process itself is saying, okay, thread number 5, it's your turn to do a little bit of stuff. The user won't notice, okay, even though each thing is actually only happening at a single point in time. Some of our modern hardware actually does allow for scheduling of threads on different CPUs. So it is possible to have one program, one process that has more than one thread, and having more than one of those threads actually getting CPU time at the exact same point in time because you have multiple cores. That's possible. Go ahead first.
So, like, in terms of, like, pop-ups and that on a computer, like internet browser, would that be spawning separate processes off or just different threads?
You hope not.
Because, like,
it would be a thread associated with the plugins.
Because I've seen computers just die because of pop-ups before.
Well, I mean, it's not dying. I would think it would be unlikely for the whole computer to die.
No,
the browser would be
down.
browser would become completely unresponsive. because now the browser
Not
is
that process.
the browser is sharing its CPU time with
So
a
many
million
threads.
pop-ups.
Okay.
Right.
So with a thread, is it still multiple processes? It's just a parent processes and child processes?
Well, but yes, but they're threads, not processes. So it's not fair to call them a process because when we think about process, we want to think about it in terms of that PCB and all the crap we have to store with it. And that's like a heavy thing. Where a thread doesn't have to keep track of hardware registers and all those things because it's never actually getting CPU time in and of itself. It's sharing upon its parent CPU time. So the parent is managing those different things at different points in time. So they're almost like, it's not unfair to call them sub-processes, but they are in fact different than a process.
Okay. So like a thread and a process are siblings, but process is the fat kid and thread's the skinny guy.
I guess I don't know what you mean by the sibling part though.
They're similar.
They are similar. They're solving a similar problem, but threads protect the rest of the operating system from getting starved from CPU time.
Okay.
You know, a single process can have a million threads, and that single process is not taking up any more CPU time than it got before.
Okay.
He's only starving himself, is the punchline. And that kind of goes hand in hand with our system call thing. Our operating systems today require administrator privileges in order to spawn off another process. Why? Well, let's think about if you're a virus writer. I think we talked about this when we introduced it. You know, in the early days of operating systems, it was trivial to crash an operating system with a, quote, virus. All you have to do is write an infinite loop that just keeps forking off processes, right?
Done.
Write an infinite loop that just forks children left and right. Okay? And what happens? All of a sudden you have a million processes running on the computer. The CPU scheduler is trying to context switch in, context switch out, and the machine's just in gridlock. Right? Can't do anything. And that's a program that's 5 lines long. Because it didn't require administrative privileges in order to pull things off. And we've seen it in our modern operating system. Sometimes you'll double click on a program and it'll say this requires, do you want to run this as administrator or something like that? Chances are programs like that are either spawning off multiple processes or doing some other secure type thing that, a lot of times like virus scanners have to run as administrator, and you kind of, the first time you run it, it asks you, do you allow this, blah, blah, blah. But
if you're on Windows Vista, it asks you every time you do
every time.
anything.
Okay, but that's kind of what's going on under the scene. Some of those applications need to be run as the administrator because only administrators can make certain system calls. Okay? They're the only ones that are allowed to make it. Let's see. What are the 5 process states? And what is each one for? So we have new, means I'm new. I was just born. Okay. We have ready. That means I am in line for the CPU. I am ready to be executed, but I'm not actually being executed. We have running. I think some people said execute. I wasn't too picky. As long as the word you used is close-ish to what you meant, that's fine. So running is the guy who's actually on the CPU. Okay, and it's not always one in our modern operating systems. When you have multiple cores, you could have multiple dudes in running states, okay, multiple PCBs, but from our perspective, we've been talking about single core CPUs in all of our examples. So it's the one dude that's running on the CPU. Okay, he's the one who's in the running state. Then we have the waiting state. So these are guys who have left the CPU who are waiting for something, probably I/O, but bottom line is they're not ready for the CPU at this point, so they're not back in line. Okay? And then finally we have the terminated state. Or end state or dead state or whatever you want to call it. Basically, I'm done. User has clicked close. I'm not getting in any more lines. Please remove me from memory. That's the point of that guy. All right, so those are our process states. Context switching. People miss this.
I did.
You did?
Did not.
Oh, I mean we talked about context switching a lot, right? Okay.
It's in the book.
Yeah. So, well, I mean, nobody reads books. Even though I gave you that. I gave you those reading assignments, but I didn't expect you to do it.
I was high on Vicodin and really bored.
I pride myself in being a fairly intelligent guy. You know,
yeah.
You could tell students to read a book. That doesn't mean they're going to do it.
After my surgery, I
Right,
was
Doc?
just sitting on the couch at home.
Did you read the book?
I needed to wait to fall asleep.
Did you actually read or just skim? Really? I'm proud of you.
Memorize every page.
I needed to wait to fall asleep. So.
That is not nearly as fun as you would think it would be, being able to memorize every page. I don't have...
Suits?
Huh?
Suits.
Yeah. No, I don't have the problem anymore, but I mean, some of you had conversations. I have a form of autism called Asperger's, and I used to have an eidetic memory, where I would read something or I hear something, I just remember it. That's why I think that was Rihanna that I heard. I don't listen to music at all, but at some point in passing, information went in an ear and it just got stored somewhere. So I used to be able to just flip through a book and almost take pictures of it, and then I could look at them during an exam in my head. It's like built-in cheating, right? But what's funny is when my memory broke. I mean, I still have a pretty good memory, but where my memory broke is when I started using a CPAP machine for sleep apnea. Because before that, I never dreamt. I never didn't dream. So now I have all this extra information, some of which isn't real, right? So now you go through life and you're not sure what actually happened and what did happen. So I can't trust my memory as much as I used to. So that's why sometimes I make stuff up.
That's why you thought we learned conversion and all that. Yeah, never
I guess that's possible. That is the type of stuff I do dream about. I dream about number conversion, hex to octal mostly, but...
I wish I had those dreams. You don't want to know what I dream about.
I don't.
There was a goat involved in last night, and fairs.
Yeah, so great. Yeah, a really good memory isn't all that it's cracked up to be. It can be distracting sometimes.
So you couldn't dream, or you couldn't remember your dream?
Couldn't dream. By sleeping. Well, sleep apnea means you wake up constantly while you're sleeping, but what comes with that pretty often is like REM sleep disorders and stuff like that, because you're never actually getting into a deep enough sleep.
Right.
So I never dreamed. And then as soon as I started on a CPAP machine, I started dreaming, and it was like very confusing for me. So I'd wake up and I'm like things seemed more real to me because I didn't have this whole lifetime of experience of differentiating real from not real. And I tend to dream about real stuff, like plausibly real stuff, not like robots taking over cities and things like that. I do dream about dinosaurs sometimes, but that's a different thing because that's more of I have little kid dreams, or I have real life dreams. Ninja Turtles. They make Aquaman.
Animated or real?
Real. It's got to be real. Yeah, I could tell the difference if it was animated. And I'd wake up and say, oh, it was an animated turtle. But no, I mean, I fought toe-to-toe with Donatello.
You fought like Michael Bay.
Yeah, right, exactly. Yeah. So for those of you who assume something was wrong with me, there in fact is.
You knew this. No surprise.
What was I talking about? Oh, context switching. So context switching is the act of a PCB leaving the CPU or coming onto the CPU. It's the unpacking of the bags when you're coming back onto the CPU, so you fill the registers back up with the old stuff so you can pick up where you left off. When you context switch off the CPU, you're packing your bags, copying over the current version of the registers. You should already have the current program counter and stuff because you've been keeping track of that as you've been going. But you're copying the current state of the registers so that you can get off the CPU because you're being kicked out. So that next time you get back into the ready queue, you can unpack your bags and pick up where you left off. Okay, so context switching is the act of either unpacking or packing your bags so that you can pick up where you left off next time you come on the CPU. Okay? Let's see, was there a follow-up part of that? Why do we need it? Well, we need it so that we can have multiple programs that are able to run on the CPU. So in a single core example, if we didn't have context switching, we would not be able to have more than one program seemingly running on our computer at once. All right, so context switching is in a single core CPU type situation is the way by which human beings are tricked into thinking more than one application is running at once because CPUs are really fast. So I think we kind of talked about context switching in the context, if you will, of a necessary evil. Okay, it's very expensive. Okay, it takes time to do the context switching. So you don't want to context switch too often, but you need to context switch often enough to keep the end user tricked. Okay? We like to, well, I say we like, human beings expect that everything that we want our computer to do, it will just do. Okay? I can promise you what we think it's doing isn't necessarily what's actually happening under the hood, but as long as we're tricked or we're faked out about it, we're relatively happy. As computer scientists, we have an interest. I know every one of you has a great, deep interest in how operating systems work, right? Otherwise, you wouldn't have been CS or IT majors. I mean, some of you sit there and you wonder, like, how are the Packers going to do this weekend? Some of you sit there and wonder, you know what? I really wonder, what's the Colonel doing this week? What's up?
Norm Macdonald.
Yeah, Norm Macdonald. Isn't he a weird Colonel? Colonel Sanders? It's like creepy.
He sounds creepy in Alaska.
Yeah. But because you know it's Norm Macdonald, it feels creepy.
True, but yeah, I really like that it's Norm Macdonald because he's just funny.
Yeah, he is funny, but the problem is he was in Deuce Bigalow, European Gigolo,
And that's what gives me
and
nightmares.
that starts doing the creepy thing when you think about finger licking good.
That's not gravy.
So, and at least half of that was a euphemism. All right. And if you haven't seen that movie, it's one of the funniest bad movies you'll ever see.
Yeah, it's really bad.
I mean, it's not a good movie, but it's hilarious.
It's really bad.
Let's see. Last one. What is the difference between the process scheduler, the long-term scheduler, and the CPU, or the short-term schedule? So the process scheduler is the dude who's in charge of getting PCBs loaded into the proper queues. Okay, based on their priority and all that stuff. So which ones are ready and how ready are you? Are you an important guy who's ready, or are you an unimportant guy who's ready? So his whole job, that long-term scheduler, is making sure folks get into the right line. All right, so kind of think about like the greeter at Walmart, but who actually has a job of sending you to the right checkout line or something like that. All right, where the short-term scheduler, the CPU scheduler, first of all, the thing I was really looking for here is that guy needs to be really fast, okay? Because he's part of that whole context switching job type thing where his goal is to have the CPU busy as often as possible, with the understanding that sometimes we're context switching, and that's kind of like the pit change during a NASCAR race, right? It's a necessary evil. We have to change the tires before they blow, okay? But we want to have it happen as quickly as possible so we can get back out on the racetrack to have the CPU actually doing stuff. That's a good analogy. Yeah. Isn't it epic?
High five.
High five. All right, so yeah, in any case, the short-term scheduler, he's going to feed off of those queues that the long-term scheduler has filled up. And he knows exactly where to go. He's going to go to the highest priority ready queue every single time and pull the guy out of there and throw him onto the CPU and kind of manage the context switching. All right, so he has a very small but important and must be really fast task to accomplish. That goes back to that NASCAR thing, because you might be the dude who's in charge of the front left tire. Fairly important or fairly small task, right? But if that guy doesn't get the front left tire on and the other three dudes do, you're going to have problems, right?
Just have a fat guy right on the back right, left, or back right.
I think you might have some drag issues. Okay, because I think when it comes, I learned about this a couple of years ago. I don't really follow NASCAR, but my neighbor is big into NASCAR, and you kind of initially think it's just like kind of a hillbilly type of thing, right? And actually, there is some interesting strategy to it. I mean, it's not super complex, but kind of when you take pit stops, and I mean, you want to finish the race on fumes and that. I mean, it is interesting making those decisions and that kind of stuff. But
you really could make a good, really good, like or PCB and like process schedule
Yeah.
analogies from
But you know, kind of an interesting thing I kind of learned from it is like I could never be a race car driver because of the weight. Yeah, I mean, I think I probably could fit into a car once you got help and used butter,
I could
right? Or the spray Pam or something. You know, so even small cars, once I'm in, I fit pretty well. It's the getting in part that's the problem.
like when you
So they
get
might
in-
need to make the windows a little bigger because don't those guys climb in through the windows?
Yeah.
So Dukes of Hazzard style, right? Yeah, we're gonna have to make the
Yeah.
window bigger, but apparently the weight's really important. You don't see a lot of fat race car drivers because that slows you down, even if it's a fraction of a mile an hour spread out over 500 miles. That's a lost race, right?
Well, most of them are really short too.
All right, like horse jockeys.
Like me.
5'11", 5'10".
Okay,
We're short.
That's average.
but is that average anymore? Like I know in the United States, isn't 5'10" supposed to be the average height? Is it really though? How many of you in here are 5'10" or ish? 5'10" ish. Who's taller than 5'10"? Yeah, so I mean, over half the class is taller than 5'10". Who's taller than 6'2"? 6'2" or taller.
I'm from a different generation than all of you by several years.
So I used to be 6'5". I think I'm about 6'4" now. So I think me and Nick are about the same height. How tall are you?
You're only like 5 years older than us, so that's not
Huh?
6'2".
6'2"? Okay.
half a
And I think women, is it 5'5", 5'6", or is it 5'4"? 5'4" is the average height. And my wife's 5'4", her sister's 5'6". You're 5'6". Yeah, I mean 5'6" for a dude is short. Yeah, I mean that's
story
really
of my life.
that's really more of a kind of a Chinese type of.
I'd be a horse jockey though.
So what if you go back to China now?
Well, I'm pretty sure. I think that's a new rule.
Yeah.
Really?
Yeah.
What, their population started shrinking?
Yeah, well, 30% of the population is like over 60 or something.
Oh, I see.
The other thing is
Too many old people
the
dying.
male to women ratio is like terrible right now.
Yeah.
Like,
That's really
Well, so now that you're allowed to have 2 kids in China, does one of them have to like? I'm sure they probably threw in like a rider that says that you can't get rid of the girls.
Yeah.
Because I think that's been a problem in China. If a family, when you are only allowed to have one child, if they have a girl and they wanted a boy, they find ways to get rid of it. That's why there's so many adoption things coming out of China.
Now they're like, nope.
Yeah, I don't know.
You need to
Yeah.
learn.
It's really strange to see Chinese guys our age interact around Chinese girls that are our age, because there isn't many Chinese girls our age, so it's like complete attraction.
Okay.
It's really interesting.
And they like swarm.
Yeah.
Is that what you're saying?
Yeah, it's kind of
It'd be
fun.
hilarious. And then they're like, American.
All right. So any questions about the exam? Make pretty good sense. Not too bad. All right. So when we leave, if you have any questions, if you think I ripped you off of points, come up and ask, and I'll clarify or give you points back if I think I screwed you over. If you think I gave you too many points, also let me know. I'll take some away.
It's only on the first 7 weeks. So.
whoever got the 22, you gave him too many.
That wasn't in here. It's another class. Actually, I had another class. There was a 3 and a 5,
Percent.
For what class?
250.
Did
Well,
they
was
not
it like 10
find
points for
term?
understanding?
10 questions, and yeah, they answered all the questions.
Did you get like 10 points for
Was
understanding?
Boolean not on there?
I don't think that was. Yeah. I mean, that exam wasn't that bad, was it?
No.
I mean, it was fair.
Yeah.
I mean, I tried to make the exams somewhat difficult, but
I
But
got like
fair.
a 75 or 80 on it. I'm horrible.
the
at
first
exams.
programming class or the second programming class.
I'm like really bad at
You have 200, 250, 300. Those are the 3 programming classes.
Is that like 1 or 2 points on the whole exam?
Well, I mean, each question was, as it was pointed out last time, my exams are almost always 10 questions. So it's 10 points per question. And really, some of those points were gifts. Like, I think they didn't know what they were talking about, but they just happened to have the correct-ish words written down. that in order to stay consistent with how I graded other people's, I had to give them points for those words, even though I was not convinced that they had any clue what was going on. Yeah, it's pretty bad. So, what are you gonna do? Okay, so any questions about this? We're good. All right, so I'll hang out for a few minutes after class, but let's kind of look ahead where we're going. We won't get too deep into anything since we only have like 5 or 6 minutes left. But
Like getting deep into
Were we
things.
going to go over assignment 10, or are we just going to leave that?
which one was assignment 10?
I'm not sure what the last one was. You said we were doing something wrong with pointers.
Something wrong with pointers. Well, I'm happy to go over it. I just need some context.
What were we doing?
Let's see here. Assignments.
I think we were doing context switch out.
So yeah, after we pick up your boat today, are we going fishing?
Well, it depends what time it is.
Okay.
Maybe we'll grab food.
Yeah. So I don't have my coat with me to go fishing, and then I figure after we pick up the boat, I'll throw my new fenders and that on my truck.
So finish context switch out method. So there was some confusion with that, is what you're saying? So I usually try to give easy assignments.
We just never went over it.
Oh.
Yeah.
Oh, that was it. It wasn't that it was necessarily hard. We just didn't cover it.
Right.
All right. Which context switch out should be in the CPU. Oh no, we didn't write that. So is it in the CPU? Oh, the CPU we put in charge of it. So context switch in. Okay, so this guy, store all the register values in the current PCB, set the current PCB to null, return the PCB that is leaving the CPU. Okay, that seems easy enough. All right, so we're going to take the current PCB and we're going to store all the current register values. So if we remember PCB here, and let me actually just close all these so I can just reopen just things that we're interested in here. All right, so a PCB currently has a linked list of register values, right? And the CPU has those register values. So for us, probably the easiest thing to do is going to be to copy those values of the registers over. So I think, oh, I know what you're talking about now with the pointer stuff. So one issue some folks had is they were actually setting the registers in the PCBs equal to the register value of the CPU, which is a pointer. So that means that, hey, I'm a PCB that just left the CPU, and now the next dude has started overwriting the registers with his values. Okay, now my values are changing. Make sense? Because I have a pointer to the actual CPU's registers, not a copy of the value that was in the register to reload later. All right, so we need to make sure we copy the values out of those registers. So let's see this here. Did we create a thing for registers? Was it in the CPU? Class register. Register has a name and it has a binary value. So probably the easiest way to handle this, the way I would probably write this for our simulator at least, it maybe isn't necessarily a performance type thing, is going to be, I'm going to make a change here to register, and we'll call this guy, it's going to return a register, and we're going to call this guy,
Go boy.
let's see, get copy. And this guy's going to create a register R, which is a new register with this dot name as the register. And then we'll say R dot binary value is equal to this dot binary value. And even though this guy's private, I'm allowed to access directly in here because I'm inside the register class. All right, and then finally I'll return R. So now we can ask a register to give us a copy of itself. And what that register will do is it will generate a brand new register with its same name and its contents as a copy. Make sense? And then we'll have that value. So now that we have that ability to ask a register for a copy, when we're context switching out in PCB, what I'm going to do is I'm going to go ahead and I'm going to say, let's see, is it, Yeah, let's just give us some quick functions since we only have 2 minutes. So we're going to say public void clear registers. It's called clear register storage. And this guy will say this dot, what do I call it, the registers or register values. This dot register values dot remove all. Is there an empty? That should work. So we'll go ahead and remove all the values from that linked list. So you could have done that, or you could just call remove over and over and over again until it was empty. And then I'm going to have a public void store register. And this guy's going to take a register as a parameter. And we will say this dot register values dot add r to that guy. All right, so we've given our PCB now the ability where we can tell him to dump the current value of his registers, the ones you used to remember. Just get rid of all of them. Then I'm going to be able to hand you one register at a time. Okay, so now we'll go into a CPU. We will go into our context switch out. This says store all the register values. Now, does the CPU have an array of register values? Yeah, we call it the registers. So we're going to say for register R in this dot the registers. So we'll go through each of those guys, and we'll say this dot the PCB dot. We need to clear the registers first before we do this. So this dot the PCB dot clear register storage. So that'll empty out the PCB. Then we'll say this dot the PCB dot what do we call it? Store register. And the register we're going to store is r dot get copy. So that'll get us a copy of that register. That make sense? So we cleared the registers, we went through all the CPU's registers, made a copy of each one, stored it in the PCB. Then we're going to say this dot, well, let's actually do PCB temp is equal to this dot the PCB, this dot the PCB is equal to null, then return temp. So that would be context switch out.
That was our homework, wasn't it? A while ago?
Yeah, that's what, were you not here 5 minutes ago?
No.
All right, that kind of makes sense?
Yeah.
So the pointer issue we had before we solved with this get copy thing.
Oh, that's
All right, questions, comments, concerns, bribes?
Could you go back to get copied?
All right, I will in a second. So have a good weekend. If you have questions about your exam, line up here and put your best grovel face on. All right, what do you want me to look at?
Get copied, just scroll up.
Oh, for a register? Yeah, all this guy did is he created a new register with the same name and then just set that register's binary value equal to the original value.
Okay.
So we literally duplicated himself in a brand new memory location.
Okay, so I know what I got was wrong there for some reason.